let's continue our section 1.2, find limits graphically and numerically. So the theorem or the definition: if f of x becomes arbitrarily close to a single number L as x approaching C from either side, the limit of f of x as x approaching C is L. So this is the notation. This is a function f of x, and as limit x approaching a particular number C and is equal to L. So let's look at our example here. I have a limit as x approaching 2. My function here is x minus 2 over x squared minus 4. As you can see, x cannot be 2. If x equal to 2, you're going to have 0 on the denominator, which means this function is undefined. So what I'm going to do, I'm going to assign x as close as 2 as possible from the left and from the right. So my 2 is over here, and if you plug 2 in, it's undefined. Now if I pick a number that's close to 2 from the left, I can start from 1.9, 1.99, 1.999. As you can see, it's getting closer and closer to 2. From the right is the same thing, 2.1, 2.01, 2.001. Now, we're going to use all this number and plug it in the formula and get the number on for f of x. So let's pick this one, this number right here. Alright, you're going to plug it in here. So you're going to have 2.1 minus 2, because that's your function. And then you're going to have 2.1 quantity square minus 4. Use your calculator, and your answer should be about 0.2439. That's what I get right here. I'm just round it to 4 decimal place. Now if you do for the rest, you're gonna get all of this number here on the bottom. This is the number. As you can see, as x approaching 2 from the left, the number is getting closer and closer to 0.25. As x approaching 2 from the right, the number also get closer and closer to 0.25. Both of them almost 0.25, but again it cannot be 2. So the limit of this function as x approaching 2 is going to be 0.25. So this is my L. Right? So let's look at the definition of non-existent of limit. So the first condition is if you have a function and f of x approach a different number from the right side and left side of C. Look at the function here. I have a function absolute value of x over x. My x approaching 0 from the left and from the right. So if x approaching 0 from the left, it means x is less than 0. Again, it cannot be 0. If it's equal to 0, my function is undefined. If x approaching 0 from the right, which means x is greater than 0. Now let's look at pick a number from the right. You can pick a number 5, for example, which is mean from the right. 5, absolute value of 5 over 5, you're going to end up with same number, with 1, because they are the same number. So it's going to be positive 1. So any number from the right, you're going to get positive 1. So let's say if 1 is here, you're going to have anything approaching from the right is going to be equal to 1. But cannot be, x cannot be 0. Now if it's approaching from the left, let's pick a number negative 2. So you're going to have same number again, negative on the left, on the numerator, and positive on the denominator. But you're going to get negative 1. Because they're the same number. 1 is positive, 1 is negative. So basically, negative 1 here. So if x approaching 0 from the right, you're gonna get 1, and approaching 0 from the left, you're gonna get -1. So these two numbers are different numbers. So the limit does not exist. That's the first condition. The second one is a function f of x increase or decrease without bound as x approaching c. Look at this function as x approaching 0. Again, it cannot be 0, it's undefined. So as is approaching 0 from the left, all right, from the left. If you pick a small number, very small number, and plug it in here, as it gets closer to 0, closer and closer to 0, your number is gonna get bigger and bigger. The graph will look like this. Now from the right, as x approaching 0 from the right, as a number getting closer and closer to 0, this number will get bigger. So your graph will look like this. So that's what it means. The function increase without bound as x approaching 0. So the limit does not exist. Now the last condition is f of x is go up and down between two fixed number. So let's say I have a function psi of 1 over x. If you try pi over 2 and all that number, you will see that the graph is going up and down between 1 and -1 as x approaching 0. So again, the limit does not exist. Let's look at more definition. Hi, let's continue our section 1.2. A formal definition of limit. So I will show you this. A lot of you who's not major in mathematics, you might not need to use this again, but if you major in mathematics, you will need to prove and probably see this again. So let f be a function defined on an open interval contain c except plausible at c. And let L be a real number, so L is a real number. The statement limit as x approaching c, f of x equal to L, mean that for each epsilon greater than 0, there exists delta greater than 0 such that this statement here. So this is how you prove that the limit of a function is equal to L. Now let's look at our example. Use the epsilon delta definition of limit to prove that the limit of a function 3x minus 2 as x approaching 2 equal to 4. If you substitute 2 in, you're going to have 6 minus 2, which is 4, but that's not the proof. So we're going to do the proof, and they specifically tell you to prove by epsilon delta definition. Alright, so you're gonna prove this statement from here. Each epsilon greater than 0, there exists delta greater than 0 such that this statement. And then you have to define what is your epsilon and what is your delta, and they have to be greater than 0. So I'm start out from for each epsilon greater than 0, follow step by step from the definition. There exists delta greater than 0 such that, so we're gonna go to here. All right, so such that 0 less than x, instead of c, as you can see, my c here is 2. All right, x minus c, so my c is 2 minus 2 less than delta, then f of x. Now my f of x here is the function, so it's 3x minus 2 minus L, again my L is 4, less than epsilon. That's how I'm going to prove it. So I have to define what is my delta, what is my epsilon, and if I have this statement complete, then I have to prove it. So what I'm going to do, I'm going to start from absolute value of 3x minus 2 minus 4 less than epsilon. Again, epsilon is greater than 0. So I'm going to simplify this. So 3x minus 2 minus 4, that is 3x minus 6 less than epsilon. Alright, now I'm going to factor out the 3. So I'm going to factor out the 3. I'm going to have x minus 2 less than epsilon. So I want to get this statement here. I want to get this statement. It's not there yet. But I know that if I divide both sides by 3, I will get this statement here. So I'm going to divide both sides by 3. So my x, absolute value of x minus 2 would be less than epsilon over 3. Alright, now I get this statement and I'm going to define that my delta is equal to epsilon over 3. So I'm going to let my delta is equal to epsilon over 3. Alright, so I have this statement. So I would have 0 less than absolute value of x minus 2 less than epsilon, less than delta, which is epsilon over 3. Then 3x minus 2 minus 4 less than epsilon. So I finished my proof. Alright, let's look at the next section.